Hi, and welcome back to Codex. Today we have Dr. Michael Catanzaro from Geometric Data Analytics. Dr. Catanzaro is an expert in topological data science. Today he will tell us about topological parallax. Take it away, Mike.
Great, thank you. Thanks for the introduction, and thank you to the organizers for the invitation to speak. I'm really excited to talk about these ideas. They're very close to kind of a lot of work I've been doing over the last couple of years. Having said that, I know that the ideas and the things I'm going to discuss in this talk are not maybe what you're typically used to seeing in this seminar specifically. In particular, I use a lot of algebraic topology in my work, and so I will try to keep everything at a very high level. I'm not going to assume you know anything really about algebraic topology or really deep learning. I hope, though, that you've seen something about topology and you have some intuition or some idea about kind of what AI means or these days. And but that's kind of all you need, is just like, being curious about the way in which AI is currently being used. And so with that, let's begin. So first of all, I just want to say there's a ton of people involved in this work. Too many people to put on the first slide, but their names deserve to be there. So in particular, this is joint with Abe Smith, Gabby Angelaro, Paul Bendish, and Nir Patel, all colleagues at GDA. This work was funded under two funding agencies. So this is part of the DARPA AIE Geometries of Learning program and the NASA NIA initiative. And so, but in particular, there's two program managers I would really like to thank, Bruce Draper and Ellen Goodlow. Fantastic, great people to work with. They asked us lots of really important questions that really pushed this work. And then, of course, we had technical discussions with other colleagues. So people at the University of Virginia, in particular, Matt Dwyer and his graduate student, Rory McDaniel, Tom Fletcher and his graduate student, Yinju Jin, our colleague, Jay Heineman at GDA, and Joey Tatro from STR. All right, so what are we going to talk about today? So I'm going to start with an example problem or two and kind of try to introduce this idea of geometric alignment, with the full caveat that I understand that, maybe you're not used to thinking about geometry in the way in which I'll describe it. So we'll try to have lots of pictures throughout the talk and keep things very high level. And I know it's being recorded, but again, if you have any questions, I'm really happy if you were to interrupt me and ask them. So having said that, then we'll move on to some mathematical background. I'll introduce the idea of persistence, or what is known as persistent homology. I'll describe our main contribution to this problem, which is topological parallax, and then we'll do some examples. There's quite a few examples at the end, so that's kind of the majority of it, is really sitting in that example section at the end of the talk. But before we start, I wanted to put this picture and this quote on the screen, because this is really the overview of the talk, is kind of understanding this picture here. So if you look at the picture, you'll see a picture of a horse, or what you might think is a horse, especially if you don't look at it too carefully. But this picture was posted on Twitter by Francois Cholet, who's a researcher at Google currently, and it comes along with this quote. And the quote says, "If you were wondering how often stable diffusion," so let me pause there, stable diffusion is a generative model, a generative imaging model. So you feed stable diffusion a prompt, a text prompt. For example, I would like a picture of a horse running through a field, and it will turn that prompt into this picture. This is what gets returned. You don't need to know anything about what stable diffusion is, what kind of generative model it is, the internal network architecture. If you know something about neural networks, that's great, but you don't have to know anything about them to understand this kind of dilemma or the talk at hand. So continuing with the quote, how often stable diffusion will give you a horse with more than 4 legs, or sometimes less. When you ask it for a photo of a horse, in my experience, it's about 20 to 25% of the time. And indeed, if you look at that picture of that horse, at first it might look like a horse, but then you see there are actually 5 legs sitting there, which is kind of bewildering. And more importantly, if you look on the ground underneath the horse at the tail end, you see kind of like a hoof, but there's no leg attached to it. And so we're really trying to understand, like, why would this happen? How does this happen? Any of us could look at this picture and immediately say that horse has way too many legs. But why does the AI model fail to see that? Why does it return this thinking it's okay, that this actually is a picture of a horse? So this is really the question that we're at. And we think that we have a way of solving it or a way of attacking it using algebraic topology. And the other thing I would just like to say at a very high level is there are tons and tons of open problems in this very applied field that I think need to be solved with very sophisticated mathematics, things like functional analysis, things like harmonic analysis. And so I'm just kind of advertising this area as there are a lot of very interesting problems here that are very relevant, that I hope more people will come and help solve. Okay, so what is the problem at large? The use of AI in our daily lives is kind of inevitable. It's coming, it's exciting, and it's also dangerous. I mean, it's exciting to give a stable diffusion the prompt of give me a picture of an astronaut riding on a horse on the moon, and it does it immediately. Like, that's kind of cool. But when you think of maybe AI in a self-driving car, maybe now a little bit more dangerous. And it's different in the ways that maybe are unexpected. And by that, what I mean is that there's this phenomenon that's been noticed, and that's that deep models, so in other words neural networks that have kind of deep architecture, they achieve near perfect statistical accuracy on available data. What that means is that the traditional notion of like underfitting and overfitting that we learn and we teach our stat students is not really relevant in the context of deep learning. There's a really great paper that stresses this point. It's very readable. It's by Misha Belkin. It's called Fit Without Fear. I think it's a great paper, and he kind of argues why, if you have a model and you're training it, which is just to say that you have a model and you're updating the hyperparameters of that model based off of new test data, or new training data rather, you might get into a regime which in traditional statistics we call overfitting. But if you just kind of keep training through that regime and you keep pushing, eventually the model will start to perform really, really well under these other metrics, things like which are called cross-validation. And so the traditional methods of saying that a model is trustworthy or not are kind of not really useful in the way that they used to be. And let me just kind of put one picture on the screen here to kind of describe what I will start to talk about, and that's like a good model versus a bad model, and we're going to quantify what we mean by that. So in the first picture on the left, you see a data set. We call it the winky face. The red points are in the data set that we care about, and the blue points are just background points, which are not. And so altogether, I guess it's a data set with labels. So you have two labels. You're the in class or the out class. So the in class is the red points. In the middle picture, you see a picture of a model, which is known as so we train a decision tree, and you don't have to know what the decision tree is or like how it works, but what you should know is that the decision tree is a classifier. And for any pixel in that two-dimensional grid, if the pixel is red, that means that the decision tree is telling you that's what it is predicting to be the in class, and the blue pixels are the out class. And similarly on the right, you have the same thing, but now for a neural network. I'm not going to assume you know anything about neural networks. If you do, that maybe will help, but you don't need to know that for this talk. But if you look at those two pictures and you compare them, I think we'd all probably agree, I would hope, that the one on the right is a little bit better fit than the one on the left, or the one in the middle, rather. The one in the middle is probably what we would traditionally call as being overfit, but we're going to quantify all of that throughout this talk. So, and again, if you have questions at any point, please feel free to interrupt me. Okay, so this is now some of my favorite pictures in the whole talk. I love these kind of like Dr. Seuss swirly figures. And so some basic definitions with these pictures to kind of get us going. So when I say a data set, all I mean is a finite set in a vector space. You could actually do everything we're talking about in a slightly more general setup that is of what's called a geodesic space. So it's a metric space in which every distance between points is realizable by a path. But you don't need any of that. And you don't actually need a generic vector space. If you don't like thinking about vector spaces, just let V be R to the n, Rn, for the rest of the talk. What is a model? By a model here, I just mean a function from that vector space to the set 0, 1. The model set is then the pre-image of 1. And we require that pre-image of 1, that model set, be what's called a solid. Or it should be the closure of an open set. So this will kind of just remove some maybe weird topological pathologies that we don't want to deal with. But it's still a pretty generic condition on the function little k here. And whenever I say model, this is what I really mean. If you have in your mind a neural network and you have its, like architecture, that's great. But all we really think of here as a function from a vector space to 0, 1. That's the level of generality we're dealing with. So in some sense, we're treating the model as kind of black box, or really we're treating it as an oracle. I can plug in points from the vector space V and I can get out a 0 or a 1, but I don't get to see the inner workings of the function K. And then finally, the concept of a void. So a void is an open set that intersects the convex hull of the model set K, but it does not intersect K. So for example, if K was the unit sphere, then the void would be the part inside the unit sphere, right? That open ball inside of the unit sphere intersects the convex hull, but it doesn't intersect the sphere. And so what we have here on the screen, these images, right, like the red points that we've sampled from this kind of cleverly drawn Dr. Seuss style surface, that's our data set. And this picture is meant to indicate a couple things, but the most important thing here is we are not assuming any kind of nice, necessarily manifold hypothesis. We are assuming that the points are certainly sampled from a distribution, but that distribution need not even be manifold. Like it can be what is referred, like a union of manifolds or even stratified. So you can have intersection points that would be non-manifold points, kind of where this Dr. Seuss hook is coming through the surface or where that sphere is sitting atop of the cone. Those kind of weird non-manifold points we certainly allow. And on the right, we have maybe what we hope is a nice model, kind of a thickening of that underlying stratified space that the points were sampled from. And you notice that maybe this model on the right, you can kind of see the curly point. There's like this curly Q in the where the points were sampled from. The model kind of smooths over that. And you can argue whether or not that's good or bad. But for example, what the model does not smooth over is the top of this cone on the right, the sphere, there is an interior, and that is not filled in. That's what that kind of circle is meant to indicate. Of course, we'll get into all of this in more detail soon, but these are the types of like ideas and descriptions that we'll be giving. So geometric alignment. How can we distinguish what I think of as a good model from those that are either too coarse or too fine? So we have this claim, and we believe that good models should match the multiscale geometry of the data upon which they were trained. The difficulty here is that we really don't know the shape of capital K. We only have access to this oracle function, and we want to understand the shape of the preimage of 1 in that function. So what we need to do is, first of all, make sense of what the heck is multiscale geometry of data. I will describe to you what I mean by that. I don't assume that you know what that means. And kind of hopefully convey to you the problems that come from models which are either too coarse or too fine. So if you look at the bottom here, we have this data set, capital A. It kind of looks like a capital A that we sampled from. The first model you see is kind of like a big gold triangle around that. That is too coarse. You cannot see the fine detailed structure of the A. You can't see the fact that the A has a hole in the top of it. You can't see the 2 legs coming down. At the other end of the spectrum, you have a model which is much too fine. The model is just a bunch of these disjoint gold circles around every data point. The model has simply memorized what is in the data set and what is not. It will have poor generalization properties. And another thing to notice here too, throughout all of this, is that we are always assuming that the data set is in the preimage of 1. In other words, we are assuming that the model is trained to 100% accuracy. That's really what we're kind of talking about. We're talking about that next stage. Okay, so you have a model and you've trained it and you got 100% test accuracy. Among all of those models, how can I distinguish good from bad? And it's very practical to assume that your model can get to that stage given the advances in deep learning, given this kind of like fit without fear perspective that I was describing earlier. We can assume that, so we do. Okay, so I'm going to go kind of quickly through this slide. again, just kind of setting up the problem here. And I just kind of want to focus on this chart at the bottom. Kind of what happens if your data set has a void, but the model doesn't see it, and vice versa. Kind of what happens if, what is a problem? Why do I need this alignment between geometry of the data and geometry of the model? What goes wrong if I don't have that? So if you look at this box, if you look at the column where it says, like, say X finds a void, but K lacks a void, what is an example of that? Well, if I go over to the right, I see the picture of the Winky data set, the Winky smiling data set, and there's black points. That's points from the original data set. And you see kind of like this open eye region of the neural network model in the bottom right. So the kind of like the top right portion of that figure. If that was all filled in orange, or kind of, I don't know what color that is, red, salmon, that would be exactly this scenario. You know, if we kind of look at that data set, you might say in the top right corner, it kind of looks like a circle. But if it was filled in, then the model would not be respecting that circle. And kind of the problem there is what happens is then the model is allowing you to interpolate between 2 points which are very far away. The model would say it's okay for you to cross the middle of that circle if the model will say we're filled in there. And why is that a problem? Well, imagine you had 2 pictures of horses, and I wanted to interpolate between them. You know, I have a bunch of horses in my training set, and I have images of horses in my dating set, and I want to generate a new one for you because you've asked me, you've typed a prompt. I could interpolate these 2, which I think are close to your prompt. And now all of a sudden, because I've interpolated 2 images, I might get an image of a horse with 5 legs instead of 4. This is kind of the problem when you allow too large scale of interpolation, when you're not respecting large scale topology, really, of the data set. At the other extreme is the top right corner of this box. If X doesn't have voids, but K finds voids, your model has voids, then your kind of model is too sensitive to noise. So this would be the case in the top right figure here, where you see kind of this ugly decision tree that looks very boxy. And if you look at the part that you might consider to be from the smile, you'll see these like kind of lots of like these little blue rectangular edge regions that are very small that the model is rejecting. The model is saying that those points are not in the inset. Those points are not pictures of horses, for example. And so the reason this is a problem is because, well, you know, it's for a variety of reasons, but simply it's not stable. I have 2 pictures which I think of as horses. I take, and they're very close together, those pictures. I can take like a small perturbation of one that's between the other one, and now I'm suddenly don't have a picture of a horse. But you and I would look at it and say, that's definitely a picture of a horse. So you kind of need both of these. And we'll see, by the way, examples of our theory applied to data sets where both of these things fail and why you should be careful about them. But yeah, again, just to try to kind of give you some high-level understanding of what's going on here. Okay, so I'll go kind of quickly through this because we don't need it, but just in case somebody in the audience has heard of TDA before. So when I say multiscale geometry, what I'm really thinking about is what's known as persistent homology. I'm going to use persistent homology to detect and quantify multiscale geometry. So what is homology? Before we put that word persistent on it, homology is a functor, which means it takes in something topological and it spits out something algebraic. For us, the algebraic things that spits out will only be vector spaces. You know, algebraic topology is a beautiful field. You know, you can study groups, rings, fields. As you vary that structure, you can say more and more precise information about your underlying space. It's a beautiful subject. We won't get into any of that. So what we'll just do is the simplest thing you can do, which is typically referred to as studying the Betti numbers of a space. So if you give me, so at the bottom of the screen here, so if you give me a topological space Y, Betti 0 is the rank of a vector space. In other words, it's just a number, and it's going to count the connected components of the space that you plugged in. Betti 1 is also the rank of a vector space. It's just the number of contractible loops of the topological space you plugged in. Betti 2 is the number of 2-dimensional voids, and you can go on and on and on. You can kind of study higher dimensional structure of your topological space that you're interested in. If you want to think now, what if I don't have just one topological space, but I have a nested sequence of topological spaces? So in other words, I have like, you know, a space Y0 contained in Y1, contained all the way up to Yn. You can take the homology of each topological space in that filtration. That is what is referred to as persistent homology. But instead of me describing that kind of general construction, let's talk about a very specific one. So suppose I'm given a data set X, and I'm going to define for you a simplicial complex. So given a data set X, I look at all subsets of X whose diameter is less than or equal to alpha. So I have some real number alpha, and I'm defining for you a space which depends on that parameter alpha. And so the common visualization we have in our minds is the following. So VR of alpha, what you do is you should put a ball of radius alpha around every point in your data set. And if two of those balls overlap, I will draw an edge between those points. And so in these pictures here, and by the way, what I just technically described is the Czech complex, not Vittor strips, but they're kind of close. So let me just blur the distinction for pedagogical reasons here. If the distinction matters, I'll make it clear. But the point is, like, as that parameter alpha increases, those balls are growing, and now more and more edges can be formed. So in the bottom left here, as I go from A to B to C, I have a sequence of inclusions. Oh, I should say what else you do. The Vittor-Rips complex is so that if you can ever fill in a simplex, you fill it in. So if you ever have the boundary of a triangle, you fill in the triangle immediately. You don't necessarily wait. If I ever have, like the boundary of a tetrahedron, so now I have 4 triangles, I fill in that tetrahedron immediately. And so you get a simplicial complex in this way. And so, I mean, that's exactly what I just said out loud. So you're given a data set X, you're going to build a space for each real number, each positive real number alpha in this way. Okay. I know that we're kind of getting down in the weeds a little bit, but I promise we'll have some pretty pictures again soon. So now, what is the idea of persistent homology? Well, instead of studying kind of like all of those spaces individually, those spaces meaning the ones where I increase the radius of the balls around each point, study it in a family together and track what's going on as a function of that radius. So in the figure on the left here, we have some original data set. It's these orange dots. And as time progresses, I grow a blue ball around each one of some radius, and I'm increasing the radius kind of in time in this picture. And what you want to do is you want to keep track of the topology. So you want to keep track of how those Betti numbers that we were just describing, how do they change as I vary alpha? How does the number of connected components change? How does the number of loops change? How does the number of voids change? And so in this figure here, by the way, on the right, you're seeing a persistence diagram for degree 1. So what the thing on the right is capturing are the loops of the thing on the left. And really, there's this lemma called the nerve lemma, which says you can work with that simplicial complex, or you can work with the union of the balls, and that's totally fine. You can kind of, the topological properties of one are equivalent to the topological properties of the other. So that's why I'm not drawing the simplicial complex here on the left, because I don't want to kind of muddy the picture too much. Instead, just look at the union. And so on the right, you see there's 2 axes. You have a birth axis and a death axis. The one that's labeled birth is kind of telling you the radius at which something new occurs for the first time. So in other words, like, when is the first time you see a cycle? The death axis, this vertical axis here, is kind of keeping track of when does that cycle get filled in? When is it no longer a non-trivial loop? When can I shrink that loop down to nothing? And so you see for a while here, by the way, like right now at these times, there's a loop in the middle that's not contractible. But as those balls get filled in, that loop gets filled in as well. And then you can see here at the very end of the animation, you have a dot with some kind of death coordinate. And these dots in the middle that are very close to this y equals x, birth equals death line correspond to like the little holes that are, kind of in the structure there. And you can see them, because they're close to the diagonal, their birth and their death parameters agree. So this is kind of like a very quick summary of what persistent homology is all about. It's about studying multiscale structure of data, or kind of anything, but multiscale structure of data in particular through the lens of homology. Okay, so this is the main tool we're going to use. This is what I mean when I say multiscale geometry. I mean understanding kind of the topology of the Vittor-Rips complex, and thinking of that as a proxy for the topology of the data set. Of course, the data set, is a finite set of points. It doesn't have topology, and so we infer that from this construction. Okay, so now what do I mean by multiscale? So I kind of like this picture. If you take nothing away, nothing else away from this talk, hopefully it's kind of thinking about this question here. How many circles do you see here on the left? If you kind of step way back, you might see one kind of big rainbowy circle. And if you kind of zoom in closer, you might see 12 individual circles, right? And the point is that with the Vittori-Rips construction, or rather with persistent homology, you can see both without making any choices. So if I take the Vittori-Rips parameter to be very small, I'll kind of, I'll see 12 circles. So right now, this simplicial complex, so I've subsampled the thing on the left, so it's not so crazy. And the thing on the right now is the Vittori-Rips complex of that with a very small radial parameter. And that space is 12 circles. If I increase the radius a little bit larger, now you can see the full global circle. You can see the organization of the 12 circles in a circle, right? The data set on the left is not just 12 circles, it's 12 circles kind of arranged in a circle itself. And so you can see that multi-scale structure. That's kind of one of the nice aesthetically pleasing things about persistent homology is you have this scale parameter and you do not choose the scale parameter. You take all possible choices. You let the parameter vary, right? We want to like kind of, stay as canonical as we can be here. So I just wanted to say that in the persistence diagram, this is this thing on the top right, this is the birth-death diagram we were just seeing. You can see both of these phenomena. The thing in the bottom left, I'm not going to describe too much. It's called the barcode. It's just you plot the XY coordinates linearly and of the points in the persistence diagram. But my point is this, that the persistence diagram captures both of these multiscale features, these phenomena. It sees the local geometry of the 12 circles, and it sees their global organization as well. You can kind of get both of that, though both of those pieces of information, you can read that off of the persistence diagram. So this is why we use persistent homology to study multiscale geometry, because it allows us to do exactly this. Okay, so now let's get back to our problem. We want to understand the shape of a data set, and we want to understand how that relates to the shape of a model. I kind of gave you some examples before of why you might want the voids in one to line up with the voids in others, but and we'll see concrete examples of that at the end. So for the time being, let's, you believe me that we want to do this. And the way that we're going to do this is by using kind of geodesics. We're going to see how do geodesics in the ambient vector space compare to geodesics that are required to stay within the model. And if we can see the deviation between the lengths of those two geodesics, then maybe we can say something about how the shape of one aligns to the other. And concretely, if you see in the top right here, you have like this thick, solid blue line that's kind of cutting through the bottom of the A. That would be a geodesic in the ambient vector space. The blue curve, right, which follows the model, which stays within the model, that is a geodesic within the model. And the fact that the curved one is longer and kind of quantifying how much longer is it than the straight line one is how we will match up shape. And so, the title of the talk starts with topological parallax. Doing this process is topological parallax. So, again, topological parallax is it's an example. It's a construct from algebraic topology. So, I'm gonna, I guess, give you the definition of it, but for this audience, I think it's better for me to just kind of describe what's going on. You might get more out of it in that way. So, we will measure how, remember capital K here is the preimage of one. It's the thing that the model says is the in class. We will measure how that model set distorts the data set's multiscale geometry only using this oracle function. And so how do we do that? We do the Vittori-Rips complex exactly as I just described. We put a ball around every point in our data set of radius alpha, and we let alpha vary from 0 to infinity, and we kind of see what's going on. This is all kind of understood. Now what we'll do is for each edge in that Vittori-Rips complex, which remember is a simplicial complex, so for each edge, we'll use the oracle now. We'll use this function and we'll say, does this edge lie in the model? we'll query the points along that edge, or the entire edge really, and see, does the edge lie in K? If it doesn't, then we do not include it in our parallax complex. But oftentimes what will happen is it won't be in the edge at that threshold in which it was before. In other words, and I'll show you a picture of this, you might have to increase the radius of the balls so that now those balls overlap in that edge. Their overlap is in the model. That's kind of the idea here. So if the edge does lie in K, we'll record the new filtration value, the new radial parameter. And importantly, this is where the whole story gets extremely complicated, the difference epsilon from its value in V. So just to make sure that we're clear here, let me go back to this picture that I just had. If I forget about anything in gold, and I'm looking in this edge in the A, right, that's got the straight line across it. If I put a ball around each of those points whose radius is exactly half the length of that line, those balls will touch, they'll, kind of tangentially kiss at one point. But that point is not in the model. And if that point's not in the model, I know the edge can't be in the model. So now I increase the radii. As I increase those balls will start to intersect in an entire like almond type shape. Until that almond shape intersects the model, the edge cannot, the geodesic between them cannot exist in the model. So that's the sense in which like it might eventually be in the model. I just have to keep growing the balls. I have to keep increasing the radius. So that's why the radius can shift. And we'll see a picture of this. And then not only do we keep track of the new value, but we keep track of how much did it shift? How much did you have to increase the radius of those balls until it became the edge became in the model K. So this is the formal definition. It's kind of exactly what I just described. Again, here's the picture I keep talking about. The length of this edge in the ambient metric space or ambient vector space is denoted d lowercase capital V, whereas the new edge is d lowercase capital K. Remember, K is the model. If you're interested in the details of this, I'm happy to come back over it, but I think in the interest of time, I'm going to kind of go fast through that slide and through this slide. So what I want to just emphasize with this slide is kind of how much more difficult the theory becomes when you introduce this other parameter. So we have two parameters now. You have the parameter upon which that you can increase the radius of the balls around each of the points in your data set. And then you have this parameter epsilon, the parameter of which how much distortion are you going to allow? How much distortion am I going to allow between an edge in the ambient vector space compared to that same edge in the model? If you're familiar, kind of, how do I say this? The reason this is hard is because now there are two parameters. So in a nutshell, if you're familiar with kind of like representation theory or representations of quivers, in ordinary persistence, you only have one parameter, the radius parameter, that kind of can increase. It lives, on 0 to infinity. What that corresponds to is a representation of a linear quiver. And representations of linear quivers are kind of easy from a representation theory perspective. We understand how they decompose. They decompose into very nice one-dimensional indecomposables. You should be thinking, like how you decompose a vector space, for example. When you introduce another parameter, now you have a vector space that depends on two parameters, alpha and epsilon. The quiver that underlies all of this whole story is no longer directed. The representation theory becomes wild in the technical sense. And so the story becomes much more complicated. So kind of throwing all of that under the rug and saying there's lots of interesting work there and there's, difficult proofs and it's a very interesting part of, research. Let me say that what we kind of have done or what we come up with is the bottom part of this theorem. So the thing that we've developed is stable under perturbations of the data set. And in particular, it spits out two numbers, lambda low and lambda high, and those are also stable. Okay, so what are those? So lambda low is a scale of locality. It's telling you that if you want to interpolate, so these are both real numbers, lambda low and lambda high are real numbers. What our machinery gives you is lambda low, the scale of locality. It says below this scale, you can interpolate as much as you want. So as long as you move off of your data set by distance less than lambda low, you're guaranteed to stay within the model. So it's kind of like a stability approach, a stability metric. So it's saying like small perturbations are totally allowed. Small interpolations are safe. So this is kind of like local geometry. We're saying the local geometry of the data set matches the local geometry of the model. At the other extreme, we also provide another number called lambda high. Lambda high is telling you when large-scale topological structure is respected in the model and in the data set. So for example, like in the figure A on the right, you see like there's this hole on the top of it, this like kind of triangle that makes the whole of the capital A. Lambda high would be telling you something about whether or not that model, that feature, that void, if that exists in the model as well as in the data set. Okay, so rather than go into kind of any more of this, I think it might be a good idea to see a bunch of pictures. And maybe this cartoon example isn't even the greatest one, but kind of, what do I want to say here? Like, you know, if you look at how the model here is this kind of orange outline, your data shape are these kind of like this snowman looking data set. And as the model, say if you go from the first picture to the second, as you dent in that left side, now you see a value of lambda low is whatever it is, but that's forbidding small interpolations. So I'm not allowed to interpolate across data points whose distance is greater than 7.1. I mean, the number doesn't matter, but you kind of see like how the non-convexity of the model over there is enforcing a restriction on how you can move between points within the model. And if you need to be careful, kind of jumping across voids. And the same is true of lambda high. But I think it's just easier to discuss these two numbers in the context of some real examples. Okay, so let's not even talk about this. Okay, great. So first example, pictures of gears or impellers, if you like. So you take a picture of an impeller and you want to count, you know, kind of some properties of it. You want to train a convolutional neural network, let's say, to determine some properties of it. What is the angle between the teeth? How many teeth does it have? What are the radii? How deep the teeth come out? What's the distance between them, etc. So kind of what goes on here. So here we have a data set. Our data set just consists of a bunch of pictures of gears. They don't all have to have 3 teeth like this one, but on this slide, but on this slide they do. So in general, our data set consists of pictures of rotating gears. They can have varying tooth depth, varying tooth width, varying inner radius, and varying number of teeth. They can have 1, 2, 3, 4, 5 teeth. So now what we do is we plug all of those images into some neural network that we've trained. It's a convolutional neural network. But again, for the context of this talk, it's just, you know, an indicator function. And in this case, we're asking it, how many teeth does my image have? So I feed it in a picture of a gear, and I ask it, how many teeth does it have? So we train this, and we train it to, you know, extremely high accuracy. So you can assume that the model that we have trained says that every 3-tooth gear has 3 teeth. And now what we do is we start to look at some like kind of projections of our data set. Excuse me. So for example, in the middle column here, you're seeing an isomap projection of the original data set. The original data set is, I mean, each one of these images, I believe, is 64 by 64. So it's 64 squared dimensional vector space the data lies in. And we're projecting it down so you can kind of see it a little bit better. Where the images on the left correspond to in that projection is they're color-coded exactly as you might imagine. And if you look at this, let's see here. If you look at like the red gear and the blue gear, they're very close in the sense that you just kind of take one, you take the first one and you rotate it 10.3 degrees you get the blue one. So to go from red to blue, I just rotate it a little bit. And in the middle image, you see that the red and blue dots are fairly close to one another, right? So this would be like a small scale interpolation. This would be a thing that you'd want to tell the model, like, yeah, you can interpolate between those two. They're so close, that seems reasonable. On the other hand, if you look at the second row of images here, if I go from the red gear to the green gear, I have to rotate it by 45 degrees. That's a larger perturbation. I mean, not even maybe a perturbation. That's a larger change. And if you look at the image again, you see from red to green, the midpoint between those two is this yellow point. That's kind of off the model. I mean, you can't see the image of the model in this figure, but you can kind of believe me when I say that it's not exactly what you would want. And the problem, if now we actually put some distances and we make metrics, so for the model that we've trained, we figured out that lambda low was this number, 14.62, whatever. And the distance between the red and the blue gear is 11. So that's less than lambda low, so interpolation is safe there. And the model should think that the interpolation between red and blue is still a 3-tooth gear. And in the bottom left, you see that the network does predict that. So that means that the local geometry of the model is matching that of the data. On the other hand, when we go to interpolate between the red gear and the green gear, that's a large scale interpolation. The distance between those two images is 22.9 in whatever metric. And that is greater than lambda low. So you should be extremely cautious interpreting the result from the model because that is too far of a deviation. And in fact, this model, you can see the interpolation gear, kind of on the left side, it's that yellow gear, and it looks to me like it has 6 teeth, but in fact, the model says that it actually only has 1 tooth, which is again one of these kind of like absurd scenarios. Anybody would look at that. You might say it has 3 teeth with cracks down the middle of them, but I don't think any of us would say that it has only 1 tooth to it. So again, kind of when you are interpolating too far, when you're taking too great of a deviation, and there's a mismatch then between the model topology really and the dataset topology, you should be very cautious with your model in that scenario. Let's see. Another example of us applying parallax comes from physical chemistry. So there's this kind of pretty famous data set now called the conformation space of cyclooctane. What is all of this? If you don't care about physical chemistry, that's totally fine. What is a conformation? It's just an arrangement in space of the molecule. And it turns out here that we actually don't need to know anything about the positions of the hydrogen atoms. If you tell me the positions of the 8 carbon atoms, that's sufficient for me to pin down the conformation, how this molecule is kind of sitting in 3-dimensional space. And so that what that means is that I need to record the XYZ coordinates of the 8 carbon atoms. So if you have 8 XYZ triples, that means that each conformation gives you a point in R to the 24. And if you kind of go over the data set that we were looking at, was then consisted of 6,000 points in 24-dimensional Euclidean space. So again, remember that each one of these points in 24-dimensional Euclidean space is just the coordinates of the carbon atoms. And some physical chemists did some really interesting work, and they showed that this space sitting in R24 is a Klein bottle intersecting a 2-sphere. And here's kind of a little isomat picture of it. And the only thing that you should take away from this is that here's a data set that comes from kind of, real data. It's not synthetic, and it has very interesting topology. If your model cannot conform to that topology, you should not trust that model for inferring things about this data set. And that's kind of exactly what we found out. So very briefly, we trained 2 models. The first is a 3-layer, fully connected neural network. It trains to 100% accuracy. Like I said, you can always assume now, basically, that your model can be trained to 100% accuracy. And then we trained another bespoke geometry-informed model, so kind of like a handcrafted model. And what we found was that, well, here, I can kind of show you. The model that we trained, which was a 3-layer neural network, it's like, the first thing that a data science student would do. It turns out that it has very poor properties from the perspective of parallax. You can kind of read the text on the screen, but I'm just going to explain it very quickly. Kind of what happens is what you can do is for every kind of, point in R24, you could think of that as a conformation of cyclooctane. And you can compute things like the distances between the bonds and the angles between the bonds, the torsion angles. And it turns out that for cyclooctane, those parameters are kind of fixed. There's like physical chemistry constraints that impose that. And the neural network model kind of completely disobeys that, does not respect those constraints at all. And if you look at the distribution of bond lengths, in the middle figure, kind of in salmon, you kind of expect to see, actually, excuse me, on the left, you see this histogram. This is a histogram of bond lengths from the original data set. has this kind of this nice bell-shaped curve, normal distribution, exactly what you would expect. In the middle curve in salmon, you see half of the distribution of bond lengths that were expected, that were, accepted by our geometry-informed kind of handcrafted model, which looks exactly like you would expect. The one on the right that kind of has this well shape in the middle of it, this is the distribution of bond lengths that are accepted by the model that was trained as a 3-layer, neural network that trained to 100% accuracy. And Parallax kind of predicts that this model is going to perform poorly, that you should not trust this model. It will do too large, it will accept kind of things that are too far away. And that's exactly what you see. If nothing else, you can see that the distribution, like that distribution kind of on the right, this dip and coming back up, does not look like a normal distribution. Oh, sorry. I'm just going to do one more quick example. Just images. So you have this famous data set called the Utah teapot. The Utah teapot, right, is this famous 3D rendering in computer vision. And so what we did is we took 4,000 images of the Utah teapot and we rotated it. Or that's what the data set consists of, 4,000 images of it being rotated. Then what we did is we pulled off the handle and we pulled off the spout. And we took 10,000 images of that thing being rotated, which we call the Utah jar. And now we construct a classifier, which just can you tell me, is this a jar or not? That's so it's again, like you should be thinking in your head like the winky face data set. You have an in class and an out class. We train a classifier to 100% accuracy. Is it a jar or is it not a jar? And what Parallax finds is that that model, its lambda low value, the length scale at which you are allowed to interpolate, is extremely low. So it's not allowing for reasonable interpolations. And in fact, all of these images here that you see on the left are jars. They don't have a spout or a handle, and yet the model rejects them. The model says, no, these are not jars. So you can kind of see in these examples, I hope, why large-scale deviations, you want to respect that. That's kind of like, the gear, the rotating gear example, where the model is allowing too great of scale of too large of an interpolation across a large topological feature. And in this example, you can see that reasonable kind of local geometry interpolations are being rejected as well. But these should be accepted, right? Like these all look like jars. They all look like, teapots without spouts or handles. And so to kind of wrap up, I just wanted to summarize, what we've talked about, and that's that I really think that this problem of why AI models are making the decisions they're making, it's hard and it's very important. And our contribution is to say that we think that models and data sets should kind of align with the geometry. They should have the same shape. They should have the same topology. And the way that we kind of measure that is using this tool from persistent homology, this biparameter persistent homology. And in fact, what we're working on now is turning Parallax, turning this lambda low and the lambda high into something that can be back propagated so that you can train your model so that it's forced to respect the shape. We do have code available if anybody's interested in messing around with it. It's available at that website. You can plug in your favorite data and model pair and mess around with it. And there's a paper with this that was actually describing this that was just accepted at NeurIPS, and it's available on the archive. So with that, I'll stop and thank you very much for your attention.
Great, thanks a lot, Mike. And let's all thank our speaker by clicking buttons. I'm gonna click a button.